Today I'm going to show you the steps to solving related rates questions. First of all, if you follow these 5 steps in order, you shouldn't have any difficulty going through these to the end. The first thing you want to do is draw a diagram of the situation that they're giving you. Sometimes they're going to be talking about a sphere, sometimes they'll talk about a cylinder, sometimes they'll just talk about a circle or a cube or whatever you have. Draw the diagram first and label it with the unchanging measurements. For example, maybe you'll have a sphere that has a radius of 10. So whatever the unchanging measurements are, label those. And anything that changes over time, you have to assign a variable to that. And I'll go through an example of a simple related rates question so you'll know what I mean by each one of these steps. Let's see if I can just... Okay, the second step, after you got a pretty picture drawn, then what you're going to do is list all the rates that you're given. Usually there's just one, but maybe you'll be given 2 rates. So list all rates given, and the rate that you're asked to find. Remember, when we're talking about rates, it's a rate of change, and rates are derivatives. So make sure you list all of those rates as derivatives with respect to, and this phrase with respect to is used a lot when you're taking derivatives. So I'm going to abbreviate that WRT with respect to. So if you ever see me write WRT, I just mean with respect to time. So you're going to have something like, for example, dV over dt. That means the change in volume over the change in time. Or maybe you'll have a dr dt, which means the change in the radius of a circle or a sphere over the change in time. But no matter what derivative you're taking, you're going to have a variable that you've defined up in step 1 as what is changing, and the dt is always in the denominator. That means the change in time, because these rates questions are changing a rate that's changing over time. So the dt will always be down in the denominator. The third step you're going to take is to write a formula that connects the variables in the problem, whether it's a, let me write this down, whether it's a volume formula or an area formula, whatever the formula is according to this question, you need to write a formula, which is actually an equation. That connects the variables in this problem. And don't take a derivative until you've already written the formula. You're not substituting anything, you are just writing a formula down, and after you get the formula written down, step 4 is when you take the derivative with respect to time, because this formula will have actually, this formula will have these variables in them, maybe v or maybe r, but whatever this formula is, take the derivative, and it's an implicit derivative with respect to time. So it's the implicit derivative. with respect to time, right? Back here, after you've listed all the rates given. In step 5, only after you've taken the derivative should you substitute all of the values that are known in this question that you've listed out in step 1. So substitute the known values for the rate, or maybe you'll know a couple of rates. Usually it's just one, and the variables in the equation from step 4. And then at that time you can solve for what you're looking for. You're going to be solving for a rate. All right, so those are the 5 steps that we'll refer to as we go through these related rates questions. So here's an example of a related rates question. Let's say you're blowing, you're blowing up a balloon and you figured out the rate that your breath, whoops, I got too many O's in here. You figured out the rate that your breath is going into this balloon, and you figured out that it's going into this balloon at 300 cubic inches per minute. Cubic inches per minute. So you've got a pretty good breath going there. When the balloon's radius is 3 inches, remember the balloon will start totally deflated, and as you're blowing it up, the radius will increase and increase and increase, and at some point in time the balloon's radius will be 3 inches. So at that point in time, when the balloon's radius is 3 inches, how fast is the radius increasing? So if you can imagine you're blowing up a balloon, and if it's totally deflated, when you're blowing the balloon up when it's very small, the radius will increase pretty quickly. But as the balloon gets bigger and bigger and bigger, you're still blowing at the same rate, but the radius of the balloon increases slower. The bigger the balloon gets, the slower the radius is increasing. So try to imagine that. Try to imagine blowing up a balloon at a steady rate, or the air is entering the balloon at a steady rate. It goes from something very small, and then when it gets bigger and bigger and bigger, that radius, the rate of increase of that radius actually slows down. And what I want to know is when it's exactly 3 inches, what is the rate of increase of this radius? So what are we given? Well, first of all, we're given a balloon, and a balloon is supposed to be spherical. So here's my sphere. It's not a very good one, but oh well. And what we have is we have a radius that changes because we're blowing air into this balloon. So we'll call the radius r. And we want to know when r is equal to 3. Sometimes I put in parentheses the point in time that I'm looking for. So when the radius is equal to 3, you could put 3 in parentheses if you want to, but this radius is actually changing over time. So what we're actually given is that the volume, this is a volume when you have a cubic inches or cubic feet or cubic any dimension per time, that's a volume. So we have a change in volume over time. So what we're given is dV, the change in volume over the change in time is actually equal to 300 cubic inches per minute, right? You see the volume and you see the time. So now what we have is we have a volume, we have a radius, and we want to get some kind of a formula. We're in step 3 right now. We want to find some kind of formula that relates the volume to this radius. Well, the volume of a sphere, I'll put V and then I'll put sphere down here because that's what we're finding the volume of. So you remember from yesterday, the volume of a sphere is 4/3 times pi times r cubed. So that relates this volume here with this radius here. So that's our formula in step 3. You're not substituting anything in at step 3 because step 4 is next. You have to take the derivative. It's an implicit derivative of these variables with respect to time. So when we take the derivative of this V volume, we get dV with respect to time is equal to 4/3 pi, which is a constant, times the derivative of r cubed is 3r squared dr dt. Oh, back in step 2, what are we looking for? We're looking for how fast is the radius increasing. So step 2 should say, I don't know, I am trying to find dr, the change in the radius, over the change in time. So that is our, that's the thing that we're looking for, is dr dt, which is this variable right here. So after we've taken the derivative, we can simplify this down a little bit because we have a 3 in the numerator and a 3 in the denominator, so those can cancel out. And so what we're left with is 4 pi r squared dr dt. So now we can substitute, we're in step 5, we can substitute the known value. Well, the known value for dV dt is 300 cubic inches per minute. That's equal to 4 pi r squared. So 4 pi, the r we're given as 3 squared, and what we're looking for is dr dt. And now what we have to do is divide both sides by 4 pi times 9. Well, 9 times 4 is 36. So 300 divided by 36. Now this radius is in inches, so this is inches squared. So we have inches cubed per minute divided by inches squared because that's this, this 3 squared right here. And now it's time to, whoops, when I forgot my pi here. So 300 divided by 36 pi is equal to dr dt. So now I just pull out my calculator and I put in 300 divided by, make sure you open up parentheses when you do divided by 36 pi, otherwise it would take the pi and move it to the numerator and you'd get the wrong answer. So it looks like 2.653 if you rounded it to 3 decimal places. It doesn't say how to round it, so by default we'll just round this to 2.653. 2.653, and what are the units? Well, inches cubed over inches squared becomes inches, and then per minute. That's the change in, that's the rate of change of the radius. So the radius is actually increasing by 2.653 inches per minute at that point in time where the radius is equal to 3. And you could calculate the rate of change at any radius value by plugging in a different value for r. So if you wanted to find out the rate of change of this radius when the radius is equal to 1, you just plug in a 1 in here for r, and you get 300 divided by 4 pi, or plug in a 2 or whatever number you want. But this particular moment when the radius is equal to 3, there's your rate of change of the radius. So that's a very typical question for related rates. Here's another really typical question. It's called the ladder sliding down the wall. So here's another example of related rates. An 8-foot long ladder leans against the wall. Let me zoom in a little bit on this. And let me see if I can focus this. Okay, so an 8-foot ladder leans against the wall. The top of the ladder is sliding down the wall at a rate of 2 feet per second. How fast is the bottom of the ladder moving along the ground? At the point of time where the bottom of the ladder is 4 feet away from the wall. So the first thing we want to do is draw a picture of this situation. So here is our wall, and here's the ground, and here's the ladder leaning against the wall. And what's happening is this ladder is falling down the wall in this direction. And when it falls down the wall, because this ladder is a rigid 8-foot, so this is not changing at all, so I'll just label this as an 8-foot rigid ladder. It's moving, the bottom of the ladder is moving in this direction. So as the ladder gets further and further and further down the wall, the rate that the ladder is moving in the x direction is changing. It's getting faster and faster. Well, we'll see that when we plug in some numbers here. So what we have to do is start labeling the things that are changing and the rates that we're encountering. So right here, if we look at this, we've actually got a triangle situation here. And this triangle, this part of the triangle is changing. So we'll call that x because it's in the x direction. This part of the triangle is changing also, and we'll call that y. It changes over time. And what we're given is we're given the change in y because this y value is getting smaller and smaller and smaller. So what we're given is dy dx. Well, y is getting smaller, so dy dx is actually a negative value. If this ladder were rising up and making y get bigger and bigger, the dy dx would be, I'm sorry, dy dt. Oh, it's over time. Sorry, there's my first mistake. Maybe it's my second mistake. Who knows? So dy dt is negative. And what is the rate that they told us? They told us it was at 2 feet per second. So dy dt is negative 2 feet per second. They want to know how fast is the bottom of the ladder moving along the ground. So they want to know this speed here. Well, the x value is actually increasing. So they want to know what is dx dt. We don't know what that is. That's what we're trying to find out here. And it's at the point in time when the ladder is 4 feet from the wall. So at the point in time where this x is equal to 4, we want to know what that dx dt is. So now what we need to do is relate these variables that we've got drawn in this diagram. Well, because this is a right triangle, we have a formula that we can use. X squared plus y squared is equal to, now 8 is a constant, so we can call that 8 squared, just the Pythagorean theorem. So once we've got the formula written, we don't substitute anything until we take the implicit derivative. So now what we're going to do is take the derivative of this whole function, well, it's not a function, but this whole equation with respect to t. So this becomes 2x dx dt plus 2y dy dt is equal to, well, the derivative of 64 is just 0. So there's our derivative. And after we've taken the derivative of this implicitly, then it's time to substitute the values in and find what we're looking for. Well, we're looking for dx dt, which is this value right here. Whoops, gosh, you can't even see what I'm writing. So we're looking for this dx dt value, which means that everything else can be substituted in for. Well, the x we substitute in with a 4 because we want to know at that point in time where x is equal to 4, what is dx dt? So we'll substitute that in. 2 times 4 times dx dt, which we'll figure out in a minute, plus 2 times y. Well, when x is equal to 4, we can solve this for y because this 8 never changes. So when x equals 4, we can just do 4 squared plus y squared is equal to 8 squared, just a Pythagorean theorem to find out what y is equal to. Well, y squared is equal to 64 minus 16. 64 minus 16 is 48. So y is equal to the square root of 48, which is 16 times 3 is 48, so 4 square root of 3. So now we can plug that in for the y value because when x equals 4, y is equal to 4 square root of 3. dy dt was given to us at -2 feet per second. And these x and y values are also given in feet, so we can probably put a 4 feet here and 4 square root of 3 feet in here too, and so that's equal to 0. So we'll clean this up a little bit. This is 8 dx dt, and 2 times 4 is 8, times -2 is -16 square root of 3 is equal to 0. So now we're going to just solve this for dx dt. So we'll add 16 square root of 3 to both sides and divide by 8. So dx dt is equal to positive 16 square root of 3 over 8, which becomes 2 square root of 3. And this is in feet per second because this is a rate of change of x. And usually we don't give those numbers in radical form, so let's just figure out what 2 square root of 3 is. 2 square root of 3, that's 3.464. 3.464 feet per second. And that's when x is equal to 4 feet. Well, if you wanted to find the rate of change of the ladder at any other distance, if you wanted to put x equals 5 or 6 or whatever, you just have to recalculate y and substitute an x and a y in there. But this is a positive value, remember, because x is increasing, and this dy dt was a negative value because y is decreasing. So those are 2 typical examples of related rates questions, and we'll practice some more of those. The one thing I want to talk about also today is in class today we were finding second derivatives of implicit derivatives, and those problems, I think it was question numbers 36 and 37, I said I would put on tape. I worked those out, and those took quite a bit of time. They probably took at least 15 minutes for me to work those out to completion, and I didn't want to make you go through watching a video of me doing all of that algebra. I thought it would be more important to get to the related rates part of this course and not do all of the algebra. So I apologize for in class today me saying that I would put that on video when it really probably wasn't the best idea. So have a good night, and I'll see you on Thursday.